Good afternoon, all the participants of this machine learning to deep learning program. So we are at lecture number 6, the lecture. Today, the first session, the title of this lecture is Network-Based Learning Algorithms, ANN to CNN and then R. So here you will see mainly the ANN part, how the artificial neural network works, what it is. And later on, I will just touch upon CNN RNN models also. And today, the second lecture, as I mentioned, will be by Dr. Aparajita Oja from IIT, Jabalpur, on mainly focusing deep learning models for detection purpose. So starting with the network-based learning algorithms, initially with ANN. So neural network, if you see, it is a broad class of models that mimic functioning inside the human brain. So because if you see any brain, that is basically a network of different neurons, they are interconnected. And in artificial neural network, people are trying to mimic the functioning inside like a human brain. We can have different classifications of ANN as per its use and so many other things. So there are different from each other depending upon one classification can be as per the problem type, which problem ANN is basically dealing. It can be prediction or classification or clustering. Second type of ANN can be depending upon structure of the model. And third type of classification we can do with respect to the model building algorithm. That means what type of training algorithm we are using. And one of the well-established algorithm is called backpropagation neural network algorithm. If we see initially the biological neuron and its components, the most important component is the cell, basically that is neuron, and it has different components. First is dendrites, they are basically receiving the information. Cell body is basically processing the information. Axon carries the processed information to other neurons. And there are synapses, basically they provide the junction between axon and dendrites of other neurons. Coming to this is a very typical component of a biological neuron, and same type of similarity you can see in an artificial neural network. So you have dendrites which are receiving the information, cell body processing, and axon is basically providing the junction or basically carrying the information to the other neurons. So here you can see in artificial neural network, you have input of numbers at p dimension from x1, x2, and xp, and all these inputs are connected with weights. This is very, very important. And then we have a weighted sum, like here I is equal to w1 x1, w2 x2, w3 x3, and so forth. Then we have here the cell body where there is activation function, which is basically converting input, the weighted sum, to output b. And this output is forward to other neurons. Here you can see direction of flow of information. So here you see receives inputs from as x1, x2, xp from neurons, from other neurons or from environment. Then inputs fed in through connections with weights. Total input is equal to weighted sum of inputs from all the sources. And this input goes to the transfer function or activation function, which converts input to output. Output goes to other neurons or environment finally. So this is the major inputs and activities of a single neuron. The activation functions which are used in ANN as a well-established activation function, it can be 10 hyperbolic or logistic. In some cases, it is used thresholding function also. So if you see here 10 hyperbolic, your data can be minus infinity to plus infinity, and output is -1 to +1. Here for logistic one, input is minus infinity to plus infinity, and output is 0 to 1. In the case of thresholding, either again input is minus infinity to plus infinity, but output is 0 or 1 depending upon the condition we have decided on the input data. The basic structure of a feed-forward artificial neural network, which is also called multi-layer perceptron. If you see single neuron is called perceptron, But when we have multiple layers and each layer has neurons, so that's called multi-layer perceptron or simply artificial neural network. So here you have input layer, which is taking the inputs, maybe here like, for example, 4-dimensional input. Then it has output, can be 2-dimensional or at least 1-dimensional. Then you have a hidden layer, which is a free parameter. And this way you can see information flow from input layer to hidden layer and then output layer. So this is a basic structure. For example, the structure of an ANN model. Now the concept of hidden layers, so we can take non-hidden layers. So there can be no hidden layer in this case. There is only input layer and output layer. Then you have here in this case one hidden layer, and then in this case you have 2 hidden layers. Or we can have more hidden layers also. A couple of things we should know that there is no connectivity within within neurons of same layer. You cannot jump from input layer to directly to the output layer. You have to connect the neurons to the hidden layer also if it is present. So these are a few rules we have to consider while forwarding the data in a neural network. So then next comes one particular thing is ANN model. So what a ANN model means? So what do we mean by a particular model here? So model means once we know my data is 3-dimensional, for example, and my output I'm taking 1-dimensional if number of classes are less. If number of classes are more, we can keep large, maybe more than 1 neuron. Then we have to take activation function here as a model. Here you can see the ANN is not an algebraic function. It is basically a combination of algebraic functions. So we cannot write all complete ANN as an algebraic function, but it is in component form. So components can be here input neurons in the input layer, then hidden layers, then neurons in the hidden layer, then output neurons in the output layer, and the weights for each connectivity. So once we define these parameters, we can say we are fitting ANN model, specifying the values for all those parameters. Then here we can see more about an example of ANN model. If my data is again 3-dimensional, x1, x2, x3, so these are inputs going on, and my output is 1-dimensional here at the output layer, and we have taken one activation function or transfer function. So here you can see each connectivity, that is weight. So some small value has to be decided. It can be positive or negative. Then you can see the input neurons. In this case, there are 3, which is compulsory parameter. And output neuron, we have kept 1. Then hidden layer, which is a free parameter, we have kept here 1. And number of neurons in the hidden layer is 2. So these are the free parameters. So we have to, and the weights for each connectivity, there are weights. So we have to decide the weights. We have to decide the hidden layers and the hidden layer size. Then here we can see how the values are predicted or how the values are moving in ANN model. For example, I take a training data of water, which where from first band it is 1, from second band it is -1, and from third band it is 2. Now, if you see the input is coming to this neuron from 3 first neurons, and this is the weighted sum, 0.2. Here you can see we have calculated the weighted sum. This weighted sum is going in the activation function. Suppose it is logistic one, ex upon 1 plus ex. So here output I got 0.55. Same way here, we have to calculate here weighted sum, which is coming 0.9, which is going in the activation function, then output is 0.71. Then here again, these outputs are working as an input to this neuron, and we calculate the weighted sum, and then finally the output is coming 0.478. For this, we can fix the target value, suppose 0.5, and then we can find out the predicted error between the difference between output and the target value. And here we got error is 0.022. So here with this, you can see the process how this data is moving in ANN model. And whatever output we get, we have to compare with the target value. And from that, we get the error. If error is not acceptable, we have to reduce the error through training. So here we can see the how to build a model. So question is how to build a model. Once we know the input data, which is 3-dimensional, and my output is one dimensional. And if I take activation function, logistic or time hyperbolic or maybe any other, maybe like ReLU and so forth. So here we have to fix my input neurons because my input data is 3-dimensional. So 3 neurons in the output neurons, 1. Then hidden layer is a question mark, and the neurons in the hidden layer is again a question mark, which are, so there is no fixed strategy for this. So by trial and error, we should fix the number of hidden layers and the neurons in the hidden layer. The thumb rule is that there should be double the neurons in the hidden layer, which is compared to output neurons. So whatever neurons are present in the output layer, we should double the neurons present in the hidden layer. That is a thumb rule we can follow as per the past experience. So then again, for each connectivity, we have to decide the weights. Question mark is how to get the weight. Randomly, we can assign the weights. So this way, we create the architecture of ANN model. Then we take the training data, and from training data, we get output here VI, and then target value is YI. We can compare both to get the error. If this error is not acceptable, we have to decrease this error during learning, during training rather. So here we can see how to train the model. Once we have the error, how to train the model to reduce the error. So start with a random set of weights. For each connectivity, we have to give the weights, take the training data, get the output value VI, get the error. When you compare with the target value, now adjust the weight so that this error is reduced. So we have to adjust these weights so that this error is reduced at first iteration. And then we can go for second iteration and again keep repeating, and we can have number of cycles overall so that finally error is very small, which is acceptable. So here when we are firing the training data, it is feed forward. And when we are adjusting the weights, then we are applying say training algorithm back propagation, which is well established. So it is adjusting the weights from output layer to hidden layer. First, these 2 weights are adjusted. And then after that, weights between hidden layer and input layer. So these 6 weights are adjusted. So this way the weights are adjusted. Once weights are adjusted, again you fire the same training data, calculate the error. If error is not acceptable, again adjust the weight. So this way the number of iteration goes on till we found that error is acceptable. Bit more details on the back propagation. Here you should note down each weight shares the blame for prediction error with other weights. Back propagation algorithm decides how to distribute the blame among all the weights and adjust the weight accordingly. A small portion of blame leads to small adjustment, and large portion of blame leads to large adjustment. So here we are getting error, and how this error is adjusted. The weight, each weight is basically giving the error. Some weight are giving less error, so they require small adjustment. And some weights are giving very large error, so they require large adjustment. So that way the back propagation algorithm works. Mathematically, we can see how these weights are adjusted. So if I make a same ANN model here. So first you have to see the connectivity at the output and the hidden layer. So we got the output here OK. Target value is TK. And error achieved here is delta K. So here we can find out delta K is equal to OK into 1 minus OK into TK minus OK. So this way we can find out error at the output layer. So once we go get the error at the output layer, you can see the weight adjustment factor delta W is equal to eta delta xi. So eta is learning rate. Its value is more than 0. And this is constant for complete model. Delta K we have already calculated here. And xi is the input. So here whatever output we got it, that works as input to this neuron. So from here we can take input x11 and then x12. And for these connectivities, we have weights which was randomly assigned. So say W11, W12. Now, if you have to make adjustment for W11, so we have to find out delta W11. That will be eta delta K x11. Like this, we can adjust the weight for W11. Same way for W12, we can find out the weight adjustment factor eta delta K and X12. So this way the weight can be adjusted for W12. Once this is adjusted, we have to go for the hidden layer to input layer. So for this neuron, first we can focus. We are getting here OH1 output and here OH2 output, right? So here if you see for weights between hidden and the output layer, the error is delta H. So here we have to find out error at is delta H1 because this first neuron, and here delta H2. At this point as OH1 and then you can get here delta H1. Same way you can find out here delta H2. Same way. So this way you get the error at these 2 points because on the hidden you have 2 neurons. So at both the neurons you have to calculate the error. So error we got delta H1 and delta H2. For using delta H1 you can adjust these weights. And let me just take one more color. For this weight you have to take delta H2. So like this, all these weights are adjusted. Then again fire the same training data and get the output, check the error. If error is not acceptable, again repeat these steps. And like this, you can iterate number of times so that you get the very acceptable error. Second factor, if you see in ANN, there is a adding momentum. So momentum is also a factor which is added in ANN, which controls the which basically increases the speed along the local minima at particular class error location. It increases the speed and also it increases the speed along the flat region. So the momentum value generally is 0 to 1. And if you add the momentum, the weight adjustment factor delta W at n plus 1th iteration is equal to eta delta input value plus you have one more factor alpha into weight adjusted at the previous iteration. So this way you get the final weight adjustment once you're considering eta as learning rate and momentum. So here we can see the complete step for the training of the algorithm. Decide the neural network architecture, that means hidden layers, neurons in each hidden layer, decide the learning parameter and the momentum. Then initialize the network with random weights at each connectivity. And then feed forward the training data and you check the error. What is the error? If error is not acceptable, you adjust the error and then again fire that same training data. So you repeat number of times and at every iteration weights are getting adjusted. So once weights are adjusted, you can check that it is converging or not. That means error is acceptable or not. So once error is acceptable, that means ANN model is trained. Now you can fire the unknown data. And it will tell in that unknown data that there is water class or not, or agriculture is not, if it is trained for all these classes. So it will tell which class is where in the image. It will classify basically the data as a thematic map data. So here just I covered a little bit on ANN. Take a 1 minute break. So here I just talked about ANN. Now we'll take you towards deep learning models and let's try to understand about deep learning models also a little bit. So deep learning, basically the very basic model I'm just talking about. So deep learning is a set of machine learning algorithms based on multi-layer networks, right? So this looks like same like ANN, where you have input neurons, hidden nodes, and the output nodes. And this model is trained maybe for cat with different photographs of cat, and then different photographs of dogs. So once this is trained for these photographs, this is very general, very basic example, what you read in the literature also. Now, once you give any unknown photograph of cat, this can tell, yes, it is cat. And once you give photograph of a dog, it can tell you this is dog. That means it is already trained with the previous photographs. And now for any photograph, it can tell the dog or cat is present or not. So here in deep learning taxonomy, you will see a few things. If it is supervised case, so here one thing, some models are working for supervised case and some models are working for unsupervised case. For supervised, it is basically like convolutional neural network, and it can be recurrent neural network, RNN. It's called RNN, and it has different versions like LSTM, long short-term memory, and it is called like CNN. So these are basic models of deep learning. And if you see for unsupervised case, you may have deep belief nets and stacked RBMs, stacked denoising autoencoders, sparse autoencoders. So these are the few models used as unsupervised. The one thing you should note down is in statistical algorithms, same algorithm you can use it for supervised or unsupervised, specifically the fuzzy models. But in ANN and deep learning, you cannot use same model as supervised or unsupervised. So there is a bifurcation. Some models are designed only for supervised and some models are only designed for unsupervised. So what is convolutional neural network? This we can see here with the few architecture as of CNN as a multi-layer ANN. Basically, if you have an input image, maybe satellite image if I'm talking about, this can be a single band image. If you apply some filters in the form of convolutional layers to generate the output. So if you apply 4 convolutional layers, so here you get 4 outputs. They are called basically 4 feature maps. Then you can go for subsampling to decrease the feature map size through max pooling or average pooling. So here you can see the image size has been decreased to be 1/4. And again, the features are 4. That means its dimension is 4, but initial dimension was 1. And further convolution has been applied and its dimension has become 6. And again, the subsampling has been applied to decrease its size so that it can be handled by the model. After decreasing, then you can have fully connected multi-layer perceptron, that is basically ANN, or called densely populated layer. Dense layer or fully connected layer, fully connected multi-layer perceptron, or just dense layer is there to classify the data. So here you have basically convolution layer with non-linear layer, that is the activation function. So each convolution layer has an activation function like ReLU and so forth. Then it has subsampling. It has 2 versions in the literature, max pooling or average pooling. And then it has fully connected layer or dense layer. And this is basically treated as supervised algorithm or supervised model. Here, if you see before dense layer is coming up, that means before ANN is coming up, there is a feature extraction here, right? That means the data is going to higher dimension in the form of different type of features after extracting through convolution layer. And here you have a classification where the extracted features are going in the dense layer which is basically a fully connected ANN model where it does for classification. So here CNN topology, you can see it is an input image, and you apply the convolution layer to generate the feature maps as the data is going to high dimensional. And then you go for shift and distortion invariance. Shift and distortion invariance, which is called subsampling layer, or in the form of max pooling or average pooling. Advantage is it decreases the image size. And here, while applying the convolutional operations, the data goes to higher dimensions. Maybe here I've just shown 4, it may go to 64, 128, right, 256 layers can be generated. And due to that only, these models are called deep learning models. So the data is not just one dimension, 2 dimension. Through convolutional operation, data goes to higher dimension, and due to that only you get the deep learning flavor in these models, and that's why they are called deep learning models. Just adding large number of layers is not the deep learning model. Please remember, right? Second, so here this is the very simple concept I've given you for CNN. And second is RNN, recurrent neural network. RNN basically use their internal state memory to process sequence of input. So here you have sequence of inputs which are processed in RNN. It is applicable to tasks such as unsegmented, connected handwriting recognition or speech recognition. In RNN, all the inputs are related to each other. So here you can see this is the input going. It is giving some output. Some output is again going in the same model. It is repeating again. It's recurring basically. So here you can see more simple way this input. Some output is going here as a H0, and some output is going to the next iteration, or you can say next model. Then further it is taking input. It is generating output as H1, but it is also giving one node as a output to be treated as input. So it is basically recurring. It is taking the output as an input. That is the beauty of RNN. So this way it differentiates with respect to CNN. So it is basically, it has one more modified version like LSTM, which we have explored, long short-term memory, or it has GRU also. So it has 2 different variants, GRU or LSTM. LSTM we have explored with CNN or just without CNN. Some issues for large training data for learning algorithm. So there are issues that it requires large training data for learning algorithm. It can be ANN. For ANN, if you are working, it may require minimum 80 to 100 samples per class. But if you see CNN RNN, it may require sometimes 3,000 to 30,000 samples to train it. So question is where to get such a large training data, specifically in remote sensing image domain. In the conventional photography, you may have large number of photographs of different objects, number of times you can repeat, and you can train with respect to large number of photographs. But in the case of remote sensing image, you may have one image of Dehradun, and from that only you have to train the model and you have to classify. The question is how to get large number of samples. So sometimes we can generate the small chips as sample data for remote sensing, and still these chips may not be sufficient and they may not provide homogeneity within samples. So what we have proposed here, we have developed a technique that using just very simple, very seed samples of say 40 to 60 seed samples, we can extend these samples and to say 3,000 to 30,000 or more number of samples we can extend. So how we have done, we have taken a conditional extension of training samples. So here we can find out the boundary of the samples within which they are lying for a particular class. And applying some conditional extension, we can extend the more points within this boundary. So you can see this is the seed samples, and from seed samples we have extended the samples as a red dots. So here this technique, it basically calculating the boundary of the seed samples, and within that boundary it fills more number of points. So here you can see just with 40 to 60 samples we may have 3,000 to 30,000 plus samples. Here, this is the output I'm just showing you from a Formoset image here. This is the Formoset 4-band image of east side of Haridwar. This is the Ganga River. This is a dry channel. This is the wheat fields. This is their eucalyptus plantation. grass areas and dense forest. And these are canal in the area coming from Ganga River. So here we have applied the different algorithms like FCM, first basic fuzzy C-mean classifier, possibilistic C-mean classifier, artificial neural network classification, and CNN based classification, and also modified possibilistic C-mean classifier. Here we have just tried the comparison of these different classifiers, and we found the CNN classifier is very, very homogeneous and just tackled the noise more nicely, and outputs are very homogeneous compared to other outputs. How we have done, we have we have also developed the GUI for CNN and ANN, where we can input the image with its header file. And here you can see we can create the training data. We can have training and testing and load training data, and then we can process. So here, this is the image. You can see the same image has been displayed here to generate the training. And here we can basically add the training data in the tool. And here, this is the module for ANN, artificial neural network. Here we have to load the image. And this is the training module where we can define the learning rate, epoch, hidden neurons, and so forth. And this is the testing module where we have to test the output, basically classify the output. And this is the case for CNN, convolutional neural network. Again, we can load the image. This is the training module. We can define the training data, threshold value, and epochs. And this is the module for classifying the unknown data, where we can load the, and here we can load the trained model with respect to weights. We can design the model as per our choice. We can add different combinations of convolutional layer, max pooling layer, and the LSTM layer also we can add, which is a different form of RNN. So here we can make hybrid model like CNN plus RNN. So RNN we can add in the form of LSTM. And we can have the different activation functions like hyperbolic, tangent, rectified linear unit, and sigmoid. And so this way we have tested. And further, one application, maybe you will have tomorrow dedicated lecture on GAN. And here we have tried to use the deep learning for removing the cloud. Basically, one of the version of CNN model is GAN. Basically, it is basically like generative adversarial neural network. So this, with respect to the what we have done, we have taken a pre and post nearest temporal images. So the issue was we were using one image for these images for burnt paddy fields. And when we got the one image of 27th of October, it was cloud free. But the second image, we got it of 30th of October 2019, and it was having small cloud patches. So we have tried to remove this. So we have taken this as a true image and this as a false image from where the clouds has to be removed. So after removing the cloud, we got this image. So here you can see this image has became useful to be considered as 30th of October. So here you can see the GAN model. It has basically a generator and the discriminator here. So here we are feeding the real image to the discriminator as a true image, and the noisy image as a random noise image, basically which has been replaced with a cloudy image, which has been fed in the generator to generate the false image. And this false image is checked, this is a real image or fake image. If it is a real image, then it will stop. Otherwise, it will ask the generator to create further images. So this iterative process goes on till it gets the real image from the input noisy image, which was a cloud image rather in our case. This is the UNet is the generator architecture we have used of pix to pix GAN model. And patch GAN model we have used in discriminator architecture of pix to pix GAN. Some of the models we have also explored for detection purpose, like in deep learning, like RCN, fast RCN, faster RCN, masked RCN, fused fully CNN, XGBoost, SSD called single shot detector, YOLO, you only looks once, and so forth. So these are the few models we have explored for detection purpose. And few outputs I can show here. We have tried basically to classify a very high resolution image where there are a large number of buildings, big size there was a road and boards. The problem what we found, the boards and the roads were getting classified to building when I'm applying the fuzzy based classifier. So we have applied SSD model to create the bounding boxes along these buildings. So along the bounding box, we got a mask, and within the bounding box, whatever the building portion is there, that has been classified. So with this, what has happened, the road and the boards has not been classified as building. So after detection, we have applied the fuzzy based model within the bounding box and applying the training data. So you can see we got very much good output in this. So here detection we have applied for masking, and after masking within the mask area we have applied the fuzzy based model to classify the object. Further, we have applied these deep learning models like SSD for brick links detection up to sub level that the brick links are elliptical shape, or they are rectangular shape, or they are of circular shape. And this was the result we got it. And we have also created point map, and we have also created the sub classes. They are active or non-active brick links. Okay. So here we got the point map. We also have applied the mask or CNN on the same brick links area to map them. Basically, the image we have taken from the Google Earth, which was giving sufficient information to map these brick links. Basically, brick links are the unauthorized, partial unauthorized sources which are contributing a lot of air pollution to the environment, and different gases are coming in the environment. So with this mapping information of these brick links, maybe governments can take some action against them so that they can take care that they should not contribute very high pollution to the environment. We can also extract the coordinates from this image. Once the brick links has been detected, we can get the coordinates, and these coordinates can help to locate them, where this located on the ground. We have also explored to map some hangars at some airport. So here you can see the fighter planes are parked in the hangars. So using mask or CNN, we have explored to map these hangars. As a point map also we have created, and we got the coordinates also. We have experimented to map different models of aircraft which are parked on the airport using Google Earth images, and we also got again their coordinates. With this, I'm thankful to attend this session, which was on basically network-based learning models. Mainly, I focused on artificial neural network. I just touched upon the concept of deep learning through CNN and RNN and its different versions.